We ended the last module by noticing a cool thing and a disturbing thing. We started off by noticing that, hey, if we know the frequency in a population, we have now figured out how to calculate the probability of a sample taken from that population having a range of possible frequency values. And that inference can be very reliable, and its reliability can be increased or decreased. The amount of epistemic risk we take with our inference can be managed and manipulated by adjusting the sizes of those intervals. Now that's really, really cool and very clever. Unfortunately, in the real world, that usually isn't the sort of inference we need to make. That's not our epistemic position. In the real world, we almost never know what the frequency in the population is. It's big, it's hard to count. We don't have the time or the resources. And we almost always know the frequency in the sample. That's the whole point of taking samples. So the ability to make inferences from population frequencies to sample frequencies, that doesn't look very helpful. But as I suggested, there is a fix. Statisticians and mathematicians have used probability theory now to determine the likelihood of a given sample. That is, if we know how common a property like redness is in a population, we can calculate the probability of a sample with a specific size, having any possible ratio of that property to all other possible property values. And that inference schematically looks like this. We go from an inference where we have knowledge of the population to an inference about distribution of sample frequencies that we then use to make an inference that is of variable, but usually very high reliability about the likelihood of drawing a sample with a particular that falls within a particular range of frequencies. Statistics was really born, however, when statisticians realized that this relationship between samples and populations is pretty close to symmetrical. It goes both ways under certain conditions. Given a sample with a particular frequency, then, the possible populations that could have given rise to that sample will also form a symmetrical bell-shaped curve around the sample frequency. And so we see an inference from samples to populations having the same general structure. But we're not done yet. So we can figure out from our sample frequency, right, that there's going to be a range of populations here. Right? But we still need to know how spread out or closed up that range of populations is. And to do that, we really need to know how much the sample differs from the population frequency. That is, how far is this to this side or that side? How do we do that? Well, that relationship between samples and populations was first explored, as I mentioned earlier, by Abraham de Moivre in 1733. And it was famously expanded upon by the gentleman pictured below on the right, Pierre Laplace, in his 1812 Théorie analytique des probabilités, or Theoretical Analysis of Probabilities. But it wasn't really until 1901 when the Russian mathematician Alexander Lyapunov's work clarified the importance of this relationship and gave it a more general format. Finally, to end our incredibly brief story, in 1920, the Hungarian mathematician George Polay published his On the Central Limit Theorem of Calculus of Probability and the Problem of Moments, thereby introducing the name by which we've come to know the many versions of this theorem, the central limit theorem. Here we have Alexander Lyapunov, who proved the central limit theorem under more general conditions than any of his predecessors in 2 papers published in 1901, New Form of the Probability Limit Theorem and On a Probability Calculation Theorem. So how, you might ask, do we determine the standard deviation, that is, how spread out the populations are around a sample frequency and whether or not the sample frequency is skewed one way or the other? Turns out, under most real-world conditions with samples of 30 or more, the central limit theory starts to apply, and we can fudge a little bit to make this inference. Specifically, if we take the standard deviation of our sample as an estimate of our sampling error, we can conclude that the population frequency falls within the sample frequency plus or minus the standard deviation of the sample size. And we'll be right approximately 67% of the time. The population frequency will fall within 2 standard deviations approximately 95% of the time. And so now we're in a position to both manipulate the reliability of our inferences from samples to populations and to make reliable inferences from samples to populations. In doing so, we create an interval, and standardly we use the interval that's called the margin of error. That interval around the sample frequency just specifies a range of possible values that standardly 0.95 likelihood or 95% of the time we can be confident that the population frequency will fall within that interval around our sample frequency. And that is what is sometimes called inverse inference, and how statisticians and mathematicians figured out how to leverage that relationship between samples and populations to make these robust and very interesting statistical inferences that go from samples to populations.